Hello, good morning to everybody and welcome to this class of Industrial Inorganic Chemistry, where we are talking about some of the important inorganic chemicals which can be useful for the industry as some starting material for some other reactions and also for the other industries like pharmaceutical industries or any other type of useful industries where inorganic chemicals are utilized for their production. So, what we are talking about something which is our primary inorganic materials. So, what are those primary inorganic materials? So, when we talk in terms of purely inorganic compound, what we can say that, as we all know from our early years of study, including in the school days, that simple water molecule, H2O molecule, how can we define as H2O molecule? It can be a very simple molecule, but it has large implication for the reactions, for inorganic reactions, for the organic reactions, for the biochemical transformations. So, H2O can also be considered as a primary inorganic material or compound which can be useful for many types of reactions, but we still do not know much about the useful chemistry of water, because water nowadays is very much contaminated, and from the environmental aspects we also know that water is not useful in a pure form for all these reactions. So, we can consider like this water and other inorganic acids like that of your mineral acids, hydrochloric acid, sulfuric acid and the nitric acid as our primary inorganic materials. So, if we start our discussion in this particular class of primary inorganic materials, we have to consider simply the water molecule first, then all other molecules which can come into play some important role in different reactions. So, these will see that some of these inorganic compounds which can comprise most of the earth's crust. Why we are saying all these things? Because we all know that some of these useful materials like ores and the minerals, we get it from the earth crust, because already the nature has accumulated all these materials for us, and only thing we have to know where these materials are available and how we can get all these materials for our useful purpose, for our industry, for our applications, for our day-to-day use. So, first thing what we should know, the composition of the deep mantle remain active areas of investigation. So, we should know the composition of the mantle which is available, because if we want to get these from the earth crust, such as a typical mineral or a typical ore, such as that we all know that the iron containing materials like hematite and magnetite which are available on the earth crust, and these are the two useful ores wherefrom we get iron. And we all know that the iron, this particular iron can be useful for making steel and any other types of alloys. So, knowing this particular composition of the deep mantle can be a good area of research, where we know that whether we are getting a particular ore or mineral as the iron source or the manganese source. As we all know that pyrolusite MnO2, the manganese dioxide, is also available as a natural source. So, these primary inorganic materials, we can consider them as the starting point of all inorganic industrial chemistry, and these materials can be of naturally occurring. So, all these ore and minerals are natural inorganic materials, only thing that we have to utilize it properly, and that should also be cost effective, because in a cheaper way we have to get these as the corresponding material. Even sometimes if we find that your hematite and magnetite, those are not pure iron, these are oxides. So, one is Fe2O3, other is Fe3O4. So, these two oxide materials can sometimes also be useful if we are not getting these as the pure metal as the iron. Similarly, your manganese dioxide can be a useful material. So, these are also very good and useful oxide materials. So, we should be careful when we talk in terms of this deep mantle of the earth, which is a huge source like that of your source from the ocean. So, earth crust can supply some of these useful inorganic materials for our purpose. The first thing that we have to identify the composition, then the percentage wise how much of all these materials are present, and then we try to get as the oxide materials or the pure metal ion. Similarly, along with these materials, we can have the corresponding origin from the natural origin is the carbon monoxide, carbon dioxide, carbonates, cyanides, carbides and thiocyanates. These are all typical inorganic materials. Some of them are naturally available, some we try to fix it, that means conversion. As we all know that carbon dioxide can be converted to carbonates in strong alkaline medium. Similarly, some of these ores and minerals are also available as the carbonates. If these carbonates are forming, that also give us some idea to know how the typical mineralization process is also occurring in presence of some of these metal ions, like that of our zinc carbonate. If we take the example of zinc carbonate, and the formation of zinc carbonate can take place in presence of the zinc ions only, and we all know that the carbon dioxide is available in the atmosphere. So, how nature can fix this particular carbon dioxide as carbonates for the zinc carbonate species, that we also know. So, some of these metallic ions will be available, and these metallic ions will give us some important information related to the fixing for the carbonates. And so, other anions which we can derive it from there also, that the cyanides, the cyanate, the carbides and thiocyanate, these can also form some of these ionic forms with that of your corresponding metal ion to giving you the corresponding cyanides, corresponding metal ion cyanates and the corresponding metal ion thiocyanate. So, if we go from this inorganic aspect to the modern organic chemistry, which has started during 1828 when Friedrich Holler used to convert ammonium cyanate into urea, and that time it was known to us that ammonium cyanate NH4CnO is a typical inorganic material, because we do not have anything of organic origin, and that particular conversion gave us that time the first important information that a typical inorganic compound, which is ammonium cyanate, can be converted to urea, and we all know that urea is basically have some organic origin or biochemical origin, or it is available from our biological stuff. So, the formation of urea, which is nothing but NH2CO NH2 from ammonium cyanate, is the typical area of understanding where modern organic chemistry has started developing from the typical inorganic material or inorganic compound, which is our ammonium cyanate. So, these two are very much interrelated. Sometimes we will find that the pure inorganic compound can also be useful for making some useful organic molecules or organic compounds or other organic materials. So, the name which is bearing his Friedrich Holler's name, that Holler synthesis, the first time an organic compound, if we consider urea is our organic counterpart, was produced from inorganic precursor, the salt of ammonium cyanate. So, the salt of ammonium cyanate conversion to urea gives us the first idea that we can get some of these useful transformation, that is also chemical transformations and related to some inorganic basic compound, which is our ammonium cyanate. So, how we can make this particular ammonium cyanate, that we also see, that which is not typical cyanide Cn minus, but it is CnO minus. So, how we get cyanate, and that also that corresponding ammonium salt. So, ammonium salts, the making all these things we can consider thinking from the very basic component. That means, if we go for elemental analysis of all these things, that will give us some idea about the percentage of nitrogen, the percentage of carbon, percentage of hydrogen and percentage of oxygen. So, all these things basically are coming therefore from pure nitrogen, from the carbon source, from the oxygen source and from other elemental sources. So, stepwise we will see now that how the inorganic raw materials, if we consider our carbon is your source for making your cyanide, nitrogen is our typical source for making ammonium ions or ammonia or urea, which we all know that they are useful fertilizer compounds. So, these typical source, that means nitrogen is available in air, and how we can fix that particular nitrogen for our useful purpose, that means making ammonia, ammonium salts like ammonium chloride, ammonium nitrate or urea, how we can convert these, because we have plenty of nitrogen available in air. But the technology we should know which can convert that particular nitrogen to ammonia or urea is the difficult task, and that is the typical task for studying this particular course, where we will be able to understand how the natural sources, the primary inorganic materials, so the gas molecules like oxygen, the gas molecule like nitrogen or gas molecules like carbon monoxide or carbon dioxide can be our useful primary inorganic materials from which we can get large number of other converted products which can also be useful for this industry. So, what we get now is that the different concentration of all these things, that means the chemical industry what we can have in our country in India, how they are concentrated in different zones and different areas, particularly if we consider that why the chemical industry is not many in this particular part, the eastern region of our country. That we also try to understand, because we must have the regular supply of the raw materials, and all these raw materials should be cheaply available, because if your transportation cost is very much, we cannot establish a chemical industry in that particular part. Interestingly, we can have very good sources of iron, we can have very good source of coal in this particular region. So, we can have some industry related to the iron and steel making industry, and we can have some other industry related to the metals and the metal ion processing, but the other typical inorganic chemistry based chemical industries are mostly located here from Gujarat to the Punjab, that means the western part or the northern western part of this country. And if we see that percentage wise, only the other, that means this part of the country, the eastern part of the country is only contributing 70% of these things. So, studying all these things also can give you some idea that where we can establish a particular chemical industry, and if the materials such as that petrochemical industry, if somebody is trying to establish a petrochemical industry where the petrochemicals are cheaply available or the transportation cost is less, then we can establish that sort of industry. But in terms of your typical inorganic chemicals, starting from making some acids, some other useful materials, these areas or these states which can contribute much in our economy. So, what we see also that what are those materials in terms of the inorganic bulk compounds or inorganic materials what we can produce. So, some data, because we always try to compare, is a little bit old data of 2006 and 7, where we can see that these things basically from there, this but particularly from amount, that means the carbon black, what we can consider as the carbon black, whether it is a inorganic material or a organic material. So, when it is typically a carbon black, or if we consider that we are talking in terms of the coal industry. So, this carbon black, the capacity for this utilization is that how much we can contribute or how much we can use of all these materials. So, these are only few examples. So, these are all 7 examples where the typical inorganic compounds people can produce, people can make all these things and people can sell in the market. So, one such is your carbon black, then the soda ash, that means the sodium hydroxide bearing all these compounds, then also the sodium chloride, sodium hydroxide, then the caustic potash. Similarly, the caustic soda is also there. Then liquid chlorine, whether we will be able to make some amount of liquid chlorine, as we all know, like your sodium hypochlorite NaOCl is the typical bleaching agent. Similarly, the liquid chlorine, the chlorine we all know is a gas, so it can also be available in the liquefied form. So, liquid chlorine can also be a useful material, inorganic material for different purposes. That means sometime if we consider that in an organic molecule for some useful purpose we will be making, and you can have a benzene ring, and that benzene ring, if we try to get that benzene ring for chlorination. So, that chlorination, whether we can get it directly from the chlorine gas or using liquid chlorine, that we can also see. Then aluminum fluoride. So, these examples, these are some typical examples that we will also see afterwards when we study the chapter particularly devoted to aluminum as well as fluoride. Why aluminum fluoride, which is AlF3, can be useful for this inorganic industrial chemistry. Then calcium carbide, when we all know that is a typical CaC2 molecule. So, starting from your carbon black, where you can have only carbon and the different forms like your graphite and all other. Similarly, this particular one, you have CaC2. So, the carbide anion, the C2 minus, can also be useful because we all know that it can produce nicely the acetylene gas and all other things. Similarly, the TiO2, the titanium dioxide, which is the basic component of our ore rutile. From rutile we get pure quality of titanium dioxide because it is a little bit sophisticated material. Sometimes we call them as the specialty chemicals. These are not bulk chemicals because the carbon black, soda ash and all these are bulk chemicals we use in a huge amount, and those huge amount can be utilized for a large industry, but sometimes this titanium dioxide like material can be produced in a very small scale, but the purity of these materials should be very high because these are little bit sophisticated materials. For electronic industry to any other sophisticated industry we use these as, because titanium dioxide is a very good paint material also. The paint industry, they utilize this particular titanium dioxide. So, the purity is also should be very high. So, as we move to from a bulk inorganic chemical to a specialty chemical, we always have to have some high level of quality control or high level of purity check, where you can increase the corresponding purity or the corresponding quality of the material to a high extent. So, what we get therefore, that we can have in one hand the bulk and commodity inorganic materials. So, starting from all these mineral acids, the bases, the caustic soda, the caustic potash, the corresponding ammonia and all these we can produce in a large scale or in a large amount. So, these bulk and commodity inorganic chemicals are also useful for some other industries, and those industries they buy in a huge amount because they are also using this for making their molecules, but you always require these things. As I was giving some very simple example, because your H2O molecule, I can consider it as a typical inorganic molecule because you do not have any carbon in it. So, this H2O molecule, depending upon its quality of use, so this can also be considered as the bulk and commodity inorganic chemical, though it is readily available, but we do not know the corresponding idea that how good we will be using the corresponding water for a particular reaction. Suppose making of sulfuric acid H2SO4, as we all know that sulfur which can be burned to sulfur dioxide, which can further be oxidized to sulfur trioxide, and when that sulfur trioxide is consuming H2O molecule, we produce H2SO4. So, making of this H2SO4 from sulfur is a typical process where we use water molecules for its absorption by the sulfur trioxide molecule and also the typical oxidation process. So, if we consider that the sulfur which is available from nature, that sulfur we can utilize for oxidation in presence of the available O2 from air. So, sulfur can be converted to sulfur dioxide, and that sulfur dioxide can further be oxidized to sulfur trioxide in presence of some catalyst like vanadium pentoxide. So, making this sulfur trioxide is a very useful one from the natural sources like sulfur as well as oxygen only, with little bit use of your catalyst. So, that sulfur trioxide when combining with water molecule giving you sulfuric acid. So, we will be able to make huge amount of sulfuric acid as your again a bulk or commodity inorganic chemical, because sulfur to give you sulfuric acid, and that sulfuric acid can be useful for many other industries. So, this is one such example of your bulk and commodity inorganic chemicals where you can use this for our regular use. Then natural materials. What are those natural materials? As I earlier told you that your hematite, magnetite to pyrrolosite, the manganese dioxide molecule can be your natural materials. Even your sulfur, what we just seeing that sulfur for giving you the corresponding sulfur oxidized form, the sulfur dioxide and sulfur trioxide. So, your natural material, the sulfur can also be our natural material. Sometimes what we find that if the purity or the purification process of these bulk materials what is available from the nature can be improved, we can go for the quality improvement of these materials, and those materials can be useful for giving us some other useful compound. As I just now told you that a catalyst is used for the conversion of sulfur dioxide to sulfur trioxide, and that conversion can be achieved by use of vanadium pentoxide, the V2O5. But we all know that vanadium can also be available from nature as some oxides, so which can be V2O3, the trivalent state of the vanadium oxide, which can further be oxidized to vanadium pentoxide. And if we are getting a very good quality of vanadium pentoxide, so high purity vanadium pentoxide can be available to us from the natural sources. So, we can consider it as a natural material, and that vanadium pentoxide can be useful for a catalyst, because we all know that the quality or the purity of the material which can be used for catalyst is always should be very high. Then we find that the different fine and the specialty chemicals. So, what are those specialty chemicals? So, fine chemicals means the fine chemical industry like that of your pharmaceutical industry, our perfumery industry, our food industry, everything should be dependent on these fine and specialty chemicals. As we are talking about water molecules, so if we use the same water molecule as a fine or specialty chemicals, what does it mean then? That means the quality of the water molecule should be very high. That is why we use distilled water for different types of pharmaceutical preparations, different types of making medicinal molecules, and all these what we use in a very low concentrations, because the different drug molecules, different medicines what we take in our body in the milligram scale, and sometimes it go down to microgram to the nanogram level. So, when we use a particular compound in the milligram level, so the purity of the compound should be very high. So, that is why the injectable water what we go for injection, the water we use is the high purity water, which is our typical distilled water. It has only H2O, nothing else. So, the water what we get from the bulk sources, from the ocean bed, from the river, from the ponds, which can be considered as our bulk and commodity inorganic materials. So, this is a very useful example that how we can consider, because the same H2O molecule will remain there. So, this can also be considered as a natural material. Then if we go for a high purity distilled water for our medicinal preparations like our injections, giving injections, this can also be fine and specialty chemicals. So, our simple water molecule can be a chemicals for us, because we all know that the water can also be a very good solvent for large number of chemical reactions. Then we can have functional materials, nanomaterials, catalysts and the special reagents. So, these are all coming from the aspects of inorganic chemistry. As we just seen, we have seen that these catalysts, say one example, one very useful example from our school days example is our vanadium pentoxide. So, we will be talking about different types of catalysts. These can be homogeneous catalysts, these can be heterogeneous catalysts for some special purposes. Then we can have some functional materials. So, these functional materials what we find is therefore an interesting area of study is that these functional materials what we get is for us is that it can show some useful functions. Like that of our vanadium pentoxide, we have seen the typical example just now that this is functioning as a catalyst, but if some material which is a huge material like some of our polyoxometalates, some other bulk material, useful material which can be useful for say storage of hydrogen molecule, because in our next class we will be seeing how we can get or how we can produce industrially hydrogen molecule, because hydrogen like water is a very useful material for our industry. So, if we can have a material which can be naturally occurring or which can be available from our laboratory making process, that a functional material which is useful, showing some useful function as a hydrogen storage material. Similarly, we can have some other molecule that means can be used for gas storage like carbon monoxide storage or carbon dioxide storage molecule. So, these functional materials when they are present with some say polyoxometalates like all other different oxide materials. So, polyoxometalates that we will see some of these polyoxometals how they can be utilized for storing some gas molecules. So, they can show some useful functions for this storing of these gas molecules. So, gas molecules are being stored. Similarly, some materials which are considered as nanomaterials. So, materials in the bulk and also these are fine materials because the size of these materials are important. Those are of nano sized particles. We consider these as the useful area of research also, useful area for material synthesis, the nanoparticles. Like our titanium dioxide, the example what I gave you just now, that which is also a source material from rutile ore. So, titanium dioxide what we are making and that can be produced to a very small particles as a very small particles in the nanometer scale from 1 nanometer to 100 nanometer. But as we increase the surface area of these materials, the function of these nanomaterials are also changing. So, that can be also useful for paint or different other types of useful applications, and then we can have some special reagents. So, what are those special reagents that we can know that if we can have a source of some compound. So, these special materials can be named from inorganic compounds such as some compound if we can have in our hand a typical compound. Suppose we get it from a chromium metal. So, chromium metal ion can give you something because chromium we all know that when we mix carbon to the iron material we get sometimes the steel. So, alloying process in presence of carbon or any other material. Similarly, when we put chromium, we put nickel, we get some amount of stainless steel. So, that is the alloying process, but what is a typical inorganic compound? We are not talking or we are not discussing even right now as the inorganic metal ion complexes, but these are typical inorganic compound like that of our simple table salt, the sodium chloride. So, if we can have a typical sodium chloride, but if it is not a very useful one or very useful catalyst or any other thing, we will not go for any particular naming of this compound. We can consider this as a typical compound which is the inorganic compound which is sodium chloride compound, and the usefulness of that sodium chloride can be considered. But if we have a chromium based compound like CrO2Cl2, so the person or the scientist who can use this particular compound for some useful purpose, such as one such example of that compound for use of oxidizing agent of terminal alkenes to aldehyde. This is a typical organic reaction where the terminal alkene can be converted to aldehydes, and these aldehydes can show some other useful reactions. So, CrO2Cl2 preparation, which is different from our typical chromium based compound. So, we can have the chromium ore, and from that chromium ore we can make that chromium compound like CrO2Cl2. The first thing what we should know is that how we can make this compound, and a person who is using this particular compound for some useful reaction like that of your oxidation reaction of our alkenes or alkanes or any other thing, that particular name can be given to the inorganic compound, and we can have some typical name reactions in organic chemistry what we all know. So, our CrO2Cl2 can be a typical inorganic compound. So, typical inorganic compound based organic reactions, and if this can be used as a catalyst, this can be considered as a catalyst also. But the first thing what we can know is that identification of this compound as its character in terms of its oxidation number and the number of other groups attached to this particular species we can see in our next class. Thank you very much.